Hello. Okay, in this video I'm going to show this laboratory setup for this machine dynamics uh, course exercise. So I'm just going to show you an overall view of this equipment quickly, and then I'm going to go these one by one through. So over here we have this measurement PC, an industrial PC with an amplifier for this scanning laser, which is this box in the middle. Like the name says, it's scanning, so it has a 2D mirror optics there, plus a video camera. So the beam itself that comes from this, it's a laser, as you can see, but it also films this picture for analyzing purposes. So this is an optical equipment. Benefit of normal, with respect to normal traditional piezo actuator sensor, is that this is non-contactless. So there's no contact, and there's no additional mass because of the sensor itself. And you can measure pretty much any kind of solid surface. Unlike with piezo sensors, we actually do have one piezo sensor here right now. This has a magnet attached to it, so we can use it in this case because this is magnetic steel. But imagine if you want to measure something that is composite or something else, you cannot use these ones. This is a magnetic, you can see the touches there. Okay, so this box, this is the actual sensor. Then of course we need to have some sort of input. So we have this kind of an automatic hammer here that is controlled by the PC. So it gives an impulse to the system. Other option could be that we would use some sort of shaker that gives a constant sinusoidal force. But this one is maybe more compact, and I will show later what kind of a force impulse this gives. So it's basically short one hit. I can demonstrate. It doesn't make that much sound, but it makes. And then we have this sensor here. This is actually for reference purposes, because maybe it's better to show from the PC itself. Try to get focused this one here. Okay, so now you can see the video camera sensor signal plus these dots here. These blue square boxes, this represents the mesh that we are going to measure. So we are going to measure one point at a time, and for that we do need this reference. Reference basically means that it tells when we start measuring this signal, and it's time domain signal, but afterwards we convert that to a frequency domain signal using fast Fourier transformation with this scanning software. For this piezo sensor, what we are using this time as a reference, we have it's attached to this kind of bit old but still functional amplifier. This is a charge amplifier, and then this signal is transmitted using these BNC cables back to this front end. So this is both controller and amplifier for these sensors, and there's also this generator output. So basically what this generator means in this case is that we are using this PC to create automatic excitation signal. Again, it's been transmitted to this automatic hammer here, and also for this we do have an amplifier. I forgot to show it, but it's here. It's just like the name says, automatic impact hammer controller. So this basically amplifies the signal, and we do have this kind of manual knob here that we can change manually the amplitude of the input signal. Okay, I will show the software settings and these things more detailed in a few minutes, but first I want to show what we are measuring today. So as you can see, it's this kind of a very thin, about 1 meter long, 12 millimeters in diameter shaft. Maybe it's better to show from up here. So it's basically a straight shaft, but then we do have a couple of things there. First of all, in the beginning we have this kind of it's called Rotex shaft coupling, small. Then we have this kind of unbalanced discs. Idea is that we can put some screws here and create an additional unbalance to the system. So we do have a 1, 2, and 3 discs. Then we have 2 of these. These are called bearing sleeves. And then we have this kind of bearing housings here. These are not connected now. I'm trying to move this. I don't know. Okay, as you can see, it's moving, so it's not connected to anything. We have a ball bearing there. I don't know. Can I show it? Okay, well, it's barely visible. And the ball bearing, when this is operational state, it will be fastened to this, against this shoulder here on this sleeve. So normally this bearing sleeve would be inside this bearing housing here, and then this motor would be fitted on this shaft coupling, and then we have an inverter here that we can run it between 0 and 50 Hz, that is nominal. So this is actually low speed application, but this is for demonstrations. We wanted to keep the maximum speed very low in order to increase the general safety and so on. And we have this kind of a safety cover here with transparent, some sort of a plastic protection. And I want to show that this you can move this shaft. I'm trying to get better picture here. So it's not connected to the bearing housings or anything. It's just on top of these kind of vibration isolators. So just something I put there. And okay, maybe we can start setting up this software. So I'm trying to film steady picture here, but I will be making an additional slides about these, so I will be taking screenshots from here. Can I somehow try to get... Okay, well, it's a bit shaky, but I'm going to go these settings through. This same will be on this interactive session later. So first thing what we want to do is that in this kind of a scanning thing we define something called 2D and 3D alignment. So basically what it means is that we give few points here which this laser can follow. Actually, let me do the focus there. So basically what we do is that we, maybe I can show it. Okay, well, you can see, you might be, yeah, you can see. Okay, so we basically move this point in few points, and then we say that, okay, this is where it's in the picture, and we, it's hard to show now because this already been aligned, but basically we tell this software that where is this plane, what we are going to measure, and then we do also a depth scan. This is pretty detailed, and it's relevant only for this kind of scanning machines. If you would have a multiple of those piezo sensors I showed you earlier, then you would need to use something different, maybe some kind of a CAD geometry or so. But basically we just tell what is the coordinate system for this device. After that, then we make the mesh. Again, I have already done it here, I don't want to redo it, but we just put few points where we want to measure, and then we connect those, basically make a line mesh in this case, because it's quite simple. If we would have some kind of a surface, then we would make a 2D mesh and so on. So basically no limitations. Only thing is that this one scanning head, it can measure only plane and in depth. So if we would have 3 of these scanning heads, we could measure 3D surface like a surface of a car or something like that. Then once we have the mesh done, we scan the geometry. So now basically this laser goes through. I can try to show it again from the actual. Maybe you can see now. Okay, well, it's barely visible. So the laser went all of those nodes that we already put previously into the software. So it goes through. So it basically measures the exact positions and especially the distances. That's the important part. And then I can also do this depth scan one more time, so it makes sure. So it's kind of like first 2D and then the third dimension scan. Once we have done the mesh and alignments, then it's time to go through the settings, and I try to get a more closer picture. Again, I will take screenshots from these, so it's more visible in the slides. At least now I'm seeing some kind of flickering in this camera. But basically these are the most important thing. So what we go first in this general, so we want to define that we are measuring as an FFT. There are also fast scan, don't remember what that means, and then time. So basically when we want to identify the modes, then we always basically want to have this FFT scan. Again, what this device measures, it's in time, but then it transforms that to the frequency domain. And like in any kind of measuring, we want to do some sort of averaging, because if we just take one sample, we might have some kind of noise there. I mean, we typically always have some noise. So we are measuring now 3 times and averaging based on magnitude. And we also have this kind of setting that we can remeasure some points if we have too high input signal. So basically if it's going over range, then we cannot use that for making this FFT transformation. So then once this is activated, this software, it automatically changes to higher and higher settings until it gets the good signal. So it's fully automated. This is quite nice thing. Channels, well, there's a lot of details, but basically what we have is the scanning head I showed. Then we have a reference. These are just ascending numbers here, but basically reference 1 means that it is this reference for the triggering, and I will go with later, it's over here. Then we have also another reference in. Yes, this actually I forgot to show. So let me recap quickly. So this device we can use also to read data in, but also to generate this excitation signal. So the excitation signal is amplified. Again, it goes to the hammer, aluminum hammer, and this hammer, it also has a force sensor inside, or force transducer, and that signal is fed back to the system, and that's actually stored in this reference 3. So this is very important to store this excitation signal, because when we want to do this FRF frequency response function. It means that we want to do so that we have the output of the system that divided by the input of the system, both in frequency domain. Again, this will be covered in the interactive session slides. But this is important because our excitation can be different, and especially with hammer, it is something else than constant with constant amplitude over the wide range of frequencies. So it's actually quite dependent. That was quickly about these channels. Then we have a lot of other settings, so I'm going these through. So filters, we can put some low pass, high pass filters, but at this case we don't need. Basically something, if we would have some very soft, if we would filters here and so on, but we are not using those at this point. Then there's the frequency range. Now this is very low, only 200 Hz, because I know that first three mode bending mode pairs, they are under 200 Hz. So that's why it's been selected. And then there's this other setting called FFT lines. This is just a number of, well, what this represents is that when we have some kind of a bandwidth and a certain number of FFT lines, we get this resolution. So this is something we want to have accurate enough. I would say that this is very good. It can be even more smaller, but if it's like 1 Hz or 2 Hz or 4 Hz, then it's too coarse. We cannot see that well of those critical frequencies, or actually natural frequencies in this case. One thing is that okay, we want to have this small as possible, but on the other hand, the sample time, this is now 8 seconds, so this is not terrible. But if it were like 20 or 30 seconds, then even a simple measurement would take very long. So this is kind of a finding balance, that what is the good enough resolution and sample time that is not too long. Okay, then windowing. Actually, because this is now MEA, this windowing is not that important here. So this is something that should be, I think it's covered in the lectures. But if we were measuring something doing like ODS, operational deflection measurements. Then imagine that there's some electric motor running constantly. Then this windowing is beneficial. But for MEA it's not that important. But we have this Hanning option here. That is quite good. And okay, now this trigger. So like I mentioned that okay, we are measuring multiple points, but not the same time. Not same time. They are measured in series. So we need to have some sort of way of triggering. So basically we can combine multiple points into the post-processing phase and make the mode shapes. So basically this triggering means that we can define what is the phase angle in the beginning of measurement at any given measurement points, and that is basically a basis for plotting the mode shapes. So in this case we are using reference 1. This refers to that piezo sensor I showed in the beginning. So reference is always taken from the same position, but then this measurement we go through was there 15 or so nodes that we go through, and then there are some settings that okay, we want to have a difference of 3% in the whole range. There's always, when we measure, there's always some small amount of noise. In this case it's like 0.5% or something like that roughly. So when we define that it has to be sometime like 10 times or whatever higher than what is the noise itself, then it knows that okay, this is the actual triggering, or now the impact, this excitation is given to the system. Then this was some kind of enhancement setting. This we don't normally do. And then this is one of the most important for this scanning sensor. So this is basically the resolution or the accuracy. Basically like a range. Sorry, range I was meant to say. And this is something that we it has to be tested. So this is quite small system. So range is relatively low, 10 millimeters. I mean, it could be up to 10 meters per second. So this is something that it has to be tested, that it's in good range, so to say. Like I mentioned, this PC and this software, it has this kind of integrated signal generator or function generator, and it's active, and we are doing a square wave signal that is given to the hammer via amplifier. And the important thing is that what is the frequency of this one? It's now 0.1. So this means that it gives one hit per 10 seconds. Why that is because this scanning range, it's just 200 Hz, but we have a quite relatively high number of FFT lines, which end up that we need to measure 8-second sample time. So this system measures 8 seconds as a sample, and then this excitation frequency, it has to be, period between two excitations has to be longer. So now it's 10 seconds. So basically what it means that when the measurement is started, there's this first hit, then it's been triggered and measured for 8 seconds, then there's a couple seconds of gap, then a second hit of the hammer, and then again triggered, and so on. So that's why it has to be this period between two excitations has to be longer than the sample length. Okay, now we have settings done, so we can actually start the measurement. This will take a few minutes, so I will show the beginning of that, then I will jump to the results that we already have. So I'm starting it here, and then I'm going to go to film closer to the system. Okay, I need to save it somewhere. MD, yo, scan. Okay. We need to check the. Do we have this hammer close enough? We might need to increase the excitation to the system. Okay. Now you can hear it. There's one hit per 10 seconds, so it takes some time. Okay, there was again. And again. So it's very long, this one sample here, but anyway, so we are now measuring this 1 point. Okay, it just moved to the next one. So it measures 3 samples per 1 point, and then averages and so on. And you might notice that there's some white or light gray coating here. This is this kind of reflecting spray. So it's like normal spray, but once you spray it, you can actually just remove it. Okay, okay. So it's like a dried powder. Other option is to use this kind of reflecting tape. This is actually much better than this spray, but this spray often works well enough. So this will go now through all of these points, and we can actually see how long it takes. Aha, okay, 26 minutes, yeah. So I measured this once already 1 or 2 days ago, so I will stop this now because there's no point of looking this for. Maybe I show this quickly about how how this looks in time domain. So let's wait. This measures, and the same signal, it can be converted to FFT. Let's see, can we see something here? May take a bit time. Okay. And it measures 3 per point, 1 per node, and we have 17 nodes. And based on that group of data, it will make those eigen modes. Will show those scanned modes. And reference 3, that was the hammer input, so we can check how that looks like. So as you can see, in the very beginning there's this hit, and after that basically nothing. And we can see how that looks in frequency domain. Okay, so we have something, then we have 50 Hertz. This is some kind of a noise induced from the from power cables or somewhere. I can try to show actually one more time, or let me change these settings that we have a higher frequency, like 10 kilohertz. And let's take some. Let's have one test measurement. 10 kilohertz. So I want to show how this hammer excitation in frequency domain, how it looks, because that was just from 0 to 200 hertz, so it's basically nothing was visible there. So I'm measuring a single channel is this. This is the hammer, yes. Okay, so well, it seems to be that it's not showing that much. Let's check in. Okay, it seems that it's very smooth. This is now from 0 to 10 kilohertz, and now it's in decibel scale. So it seems to be very smooth. Smooth in this case. I can try to find some sample to the this interactive session slides, an example from some other system that where this this FFT made of this hammer input is a bit different. But anyway, let's go through these results, and again I will add some better screen captures and these videos to those interactive slides. So this over here, this is very similar than I showed previously. So this is an average spectrum of all scanned points, and over here this is a still image from that camera, and then we have the mesh, is this black line, and this is in 3D. So as you can see, when we have a disk, it comes like out of that nominal line. So this is taken from the surface, so that's why it looks bit so it captures the distance from the measurement point to the sensor. So that's why it looks like that. And we have only few points there now, so this is not that dense mesh. So I can show you there were couple of rigid body modes in the beginning, so I can show quickly. This one is 2.875 Hertz. So this is pretty clear. There's some wobbling, but pretty clear translational rigid body mode. I have rotate this a bit. So this is the normal view, but I rotate it in a way like this because this measures in depth, and now we can see it better. I can show another one. There was one. Okay, this again some wobbling, but you can see that okay, this is rigid body rotation around the mass center of mass. And then there's some other frequencies, but I can show that okay, 21.9 roughly. This is clearly the first bending mode. Then the next one is 82.3, and this is a bit hard to see. Let me actually zoom back here, because we have these. I was a bit lazy. I didn't want to remove this bearing housing, so we have a kind of a not clear line of sight. And on this side, we have the housing and then the hammer, and from behind these we could measure. So we were losing few points there. So the second mode, this is not that clear, but I will add an animations this and then comparison to what finite element software gave. And then we have a third mode. This is a bit more clear, but again we are lacking some accuracy between here. So over here we have this bearing housing and then this sensor. Okay, let's see if this is still recording. Okay. So I'm not sure is this still recording. I got some messages, but basically this is in a short video how this machine works and how it can be used for measuring the frequencies, but also the eigenmodes of any system basically. So we often measure this kind of or this is not a typical kind of rotor, but rotors, sometimes motor frames and so on, sometimes complete machines and so on. But okay, thank you.